The focus of this presentation is the state-of-the-art video language foundation models. The development of video language foundation models enables video understanding tasks such as action detection and recognition to be transferred to a wide range of datasets without explicit training. Among recent literature, a video MAE adopts a high mask ratio in both encoder and decoder to make the model scalable. Violet performs explicit temporal modeling as well as masking in the visual token domain to improve results in video question answering and text-to-video retrieval. In-turn video incorporates cross-modal attention modules between the masked encoder and the video text contrastive encoder to benefit tasks such as action recognition and spatial-temporal action localization. Video COCA extends the image text contrastive captioner, or COCA, to enable zero-shot video-level tasks such as classification, retrieval, captioning, and question answering. The unmasked teacher uses the clip model as a teacher to supervise a combined vision transformer and text model. This could benefit multimodal tasks such as video retrieval and video question answering. And OmniVL combines image language and video language frameworks, which enables support for video and cross-modal tasks, including action recognition, retrieval, and question answering. Now let us look at some of these models in more detail. The paper on video MAE investigates the effectiveness of video masked autoencoders as data-efficient learners for self-supervised video pre-training. The model adopts the backbone of a vision transformer and a joint space-time attention. It uses a customized video tube masking with a very high ratio, which is the model's main contribution. The paper makes three key findings. First, an extremely high proportion of masking ratio, like 90 or 95%, still yields favorable performance for video MAE. This suggests that the temporally redundant video content allows for a higher masking ratio compared to images. Secondly, video MAE demonstrates impressive results on very small datasets with around 3,000 to 4,000 videos without using any extra data. Lastly, the paper emphasizes the importance of data quality over data quantity for self-supervised video pre-training. Video MAE with the vision transformer backbone achieves state-of-the-art performance on multiple action classification datasets. The paper also demonstrates the transferability of the model to downstream action detection tasks by transferring the pre-training on Kinetics 400 to the AVA dataset and discovering further performance increase through fine-tuning and scaling up the pre-training. The sequel of this model, Video MAE2, explores the challenge of training video foundation models with billions of parameters and proposes a scalable and general self-supervised pre-training approach. The video MAE is scaled in both model and data, resulting in a dual masking strategy, which involves an encoder operating on a subset of video tokens and a decoder processing another subset of video tokens. The encoder masking scheme is the same as the original video MAE. At the decoder, the running cell masking scheme performs on par with the original model, where a 50% masking ratio achieves a good trade-off between accuracy and efficiency. The paper also introduces a progressive training paradigm for the pre-training process, which includes an initial pre-training on a diverse, multi-sourced, unlabeled dataset, followed by a post-pre-training on a mixed labeled dataset. This progressive training approach contributes to the successful training of a video vision transformer model with 1 billion parameters. The vision transformer model achieves state-of-the-art performance on multiple action classification datasets. The evaluation includes also assessments on downstream tasks such as action recognition and spatial temporal action detection, showcasing the broader applicability and effectiveness of the proposed approach. The next paper, VIND-LU, conducts a comprehensive empirical study toward demystifying the key factors in video language model design. The paper investigates multiple factors such as spatial temporal architectural design, multimodal fusion schemes, the pre-training objectives, choice of pre-training data, pre-training and fine-tuning protocols, and dataset model scaling. Empirical study in the paper reveals that crucial design factors in video language model design include the following: temporal modeling, video-to-text multimodal fusion, masked modeling objectives, and joint training on images and videos. Based on these empirical insights, a step-by-step recipe is developed for effective video language pre-training. The proposed model achieves comparable or better results than state-of-the-art models on various video language tasks without relying on external clip pre-training. The video language model's pre-training uses a standard vision transformer trained on single frames of WebVid2M as baseline. BERT is used as the text encoder for all experiments. Following the extraction of video and text embeddings, a video-text contrastive loss, or VTC loss, is used to maximize the agreement between the paired video and text embeddings. The proposed approach progressively expands the baseline image transformer by adding more components of increasing complexity, including temporal modeling blocks, multimodal fusion encoder, additional pre-training objectives, pre-training data, fine-tuning and inference protocols, dataset, and model scaling schemes. The order of these steps is determined by the computational cost, with the most efficiently implemented steps studied first, followed by the more computationally costly steps. In the end, VIND-LU adopts divided time plus space attention and video-to-text multimodal fusion encoder. It also adopts video-text contrastive, VTC, and visual text matching, or VTM, as well as masked language modeling, or MLM, as training objectives. For the task of text-to-video retrieval, VIND-LU is compared with existing methods on 5 different datasets. The results demonstrate that it outperforms previous methods by a large margin on the multiple datasets. For video question answering, the results also show competitive performance across 4 datasets. The next paper on CLIP discusses pre-training computer vision models to predict image caption pairs using a dataset of 400 million image-text pairs collected from the Internet. After pre-training, the models demonstrate zero-shot transfer to various computer vision tasks, including OCR, action recognition in videos, geolocalization, and fine-grained object classification. The proposed CLIP model, or contrastive language image pre-training, aims to predict which image-text pairings occurred across a batch. It leverages a multimodal embedding space by jointly training an image encoder and a text encoder to maximize the cosine similarity of the image and text embeddings of the real pairs, while minimizing the cosine similarity of the embeddings of the incorrect pairs. A symmetric cross-entropy loss is optimized over the similarity scores. The CLIP model demonstrates strong performance of zero-shot transfer learning. The paper highlights that the accuracy of the original ResNet 50 model on ImageNet is matched zero-shot, without using any of the 1.28 million training examples it was originally trained on. The next model, Violet, is a fully end-to-end video language transformer that utilizes a video transformer to explicitly capture the temporal dynamics of video inputs. The paper proposes a video screen transformer for the explicit modeling of video temporal dynamics and supports flexible video language learning from both videos and static images. The video swing transformer employs 3D shifted window and learnable positional embedding to model spatial and temporal attention over video frame patches, which enables simultaneous modeling of spatial and temporal features. The video swing transformer also supports a variable length of visual inputs, including static images. Additionally, the paper introduces a new pre-training task called Masked Visual Token Modeling, or MVM, which involves the tokenization of video frames into discrete video tokens for better video representations and video language learning. The language embedder, or LE, tokenizes the language input into word tokens and embeds them into high-dimensional word representations. Then the cross-modal transformer, or CT, performs cross-modal fusion over video and word features and computes joint video language representations. The cross-modal transformer incorporates positional embeddings to differentiate between the video and language modalities, and it also includes a special CLS token in the input sequence, which is used for global video language representation in pre-training and downstream fine-tuning. Three pre-training tasks are incorporated in the workflow. They are masked language modeling, or MLM, visual text matching, or VTM, and masked visual token modeling, or MVM. Masked language modeling recovers masked word tokens from joint video language features. The visual text matching models alignments between visual and textual inputs. And masked visual token modeling uses discrete variational autoencoder to tokenize video inputs into masked prediction targets. Also, blockwise masking and attended masking are used to enhance the effectiveness of masked language modeling and masked visual token modeling. The pre-training data used for Violet consists of 3 datasets with video, text, and image sources. The system is evaluated on text-to-video retrieval and video question answering across 12 downstream benchmarks. The results indicate that Violet achieved state-of-the-art or competitive performance across all these tasks. The extension project of Violet, called Violet V2, explores the effectiveness of masked visual modeling, or MVM, in the context of video language learning. The study focuses on the video language transformer, or Violet model, and its enhancement, Violet V2, through MVM pre-training. The paper investigates different reconstructive targets of masked visual modeling, such as low-level pixel values, oriented gradients, depth maps, optical flow, discrete visual tokens, and latent visual features, and considers their impact on the downstream performance. The pre-training objectives in this paper include video text matching, or VTM, and masked language modeling, or MLM. The video text matching predicts whether an input video text pair is matched or not, and the masked language modeling predicts the masked word tokens from the surrounding context. The masked visual modeling task involves the masking of visual input patches and predicting the target features corresponding to the masked ones. The pre-training is conducted on the WebVid 2.5M dataset for 5 epochs, and the accuracy is reported on the TGIF frame for video question answering and on the distinct describable moments dataset for text-to-video retrieval. The video swing transformer, or VT, in the Violet model is initialized with video swim base pre-trained on Kinetics 600, while the language embedder and cross-modal transformer are initialized from pre-trained BERT base. The study considers 8 different multimodal video pre-training targets, including pixel, histogram of oriented gradients, or HOG, depth, flow, spatial focused image features, or SIF, temporal aware video features, or TVF, discrete visual tokens from DALL-E, and continuous multimodal features extracted from CLIP. The results show that regressing the explicit RGB colors in pixel and distilling features from SWIM-B in the SIF consistently yield gains over the baseline on both downstream tasks, namely video question answering and text-to-video retrieval. It is notable that the proposed Violet V2 outperforms Violet in all tasks including text-to-video retrieval, video question answering, and video captioning, even with only 1/37 of the original pre-training data size in Violet. Additionally, it is observed that there is no merit in combining different masked visual modeling targets, and doing so will lead to downstream performance decrease. Also, as a minor but relevant note, the paper also brings attention to the fact that focusing more on spatial details of each frame will bring about performance improvement on visual feature targets. This actually concurs with the observation that existing video language benchmarks focus more on the spatial understanding of key frames of the video, and only a small fraction actually test on temporal reasoning over multiple frames. The next paper, Intern Video, aims to establish a feasible and effective spatial temporal representation by studying popular video masked modeling and multimodal contrastive learning. The paper presents a unified self-supervised pre-training paradigm which explores both masked video modeling with autoencoders and multimodal contrastive learning. For the video part, the model adopts video MAE, which trains a vanilla vision transformer and conducts video reconstruction tasks. It employs a video encoder for spatiotemporal modeling and joint space-time attention to globally characterize spatial-temporal interaction. Notably, the model bases the multimodal structure on the pre-trained clip, and it uses Uniformer V2 as the video encoder for better temporal modeling. It also adopts an extra cross-modal transformer decoder at the end of the multimodal video encoder. The dataset for intern video pre-training is large in scale. It comprises 12 million video clips from 8 different sources in 5 different domains. The results show that this model achieves significant improvements in action understanding and video language alignment tasks, as well as demonstrates impressive zero-shot and open-set results. It achieves favorable performance in temporal action localization and spatio-temporal action localization tasks. It also performs well in video retrieval, video question answering, and visual language navigation tasks. Video CoCA is a model that maximally reuses a pre-trained image-text contrastive captioner model, or CoCA, and adapts it to video text tasks with minimal extra training. The paper finds that the generative attentional pooling and contrastive attentional pooling layers in CoCA are instantly adaptable to flattened frame embeddings. This adaptation leads to state-of-the-art results on zero-shot video classification and zero-shot text-to-video retrieval. The original CoCA model adopts a cascaded decoder design, where the bottom unimodal decoder encodes the text context with causally masked self-attention, and the top multimodal decoder uses cross-attention to align image and text. The model is trained with joint contrastive loss and captioning loss. For text representations, the CLS token from the unimodal decoder is used as a global text representation for the contrastive loss, and the captioning loss is applied per text token to learn fine-grained visual textual information. CoCA uses 2 attentional pooling layers, or poolers, to extract image representations. The benefit of this architecture design is that the pooler yields a fixed number of tokens regardless of input image resolutions. This makes the image encoder and the text decoder more modular and adaptable to other modalities. Additionally, the pooler serves as a lightweight adapter so that the pre-trained vision transformer as a backbone remains frozen for many downstream tasks. In order to adapt CoCA to video, different models after the input image encoding stage are explored. Similar to the original CoCA, video CoCA adopts the attentional pooler approach, where the temporally flattened tokens are fed into a generative pooler and then a contrastive pooler. This method allows reusing parameters from the CoCA model and allows zero-shot transfer to video-related tasks. Therefore, video CoCA inherits the pre-trained image CoCA model, and then it is pre-trained on the How-To 100M and Video CC3M datasets for one epoch. Evaluation is performed on 14 different datasets and 4 tasks. Results show that video CoCA already achieves state-of-the-art on zero-shot video classification and zero-shot text video retrieval. It also achieves strong results on video captioning and video question answering after fine-tuning.